as a function, expressed in terms of an emission coefficient, which is the counterpart to the absorption coefficient. So if there is anything in what I'm saying that seems a bit hard to follow or understand, you'd stop me and I'll try to explain a bit better. Okay, I think this should be familiar to you by now. We are splitting the variations of the specific intensity in terms of an absorption part and an emission part. So that in the end, we write this is the equation of what I was meaning to get at. We write then this variation in terms of the emission coefficient which has got two parts, and a part which is linked to the absorption and another part which is linked to the scattering. That's the case for a continuous medium, and for a discrete medium, we can use the same form of the radiative transfer equation, except that now we use the Einstein coefficients, and the Einstein coefficients are related to each other by detailed balance. The emission coefficient then is a function of A, the spontaneous decay, and the absorption coefficient is then related to the coefficient for absorption, stimulated absorptions, and stimulated emissions. Okay. Any questions about the Einstein coefficients? I mean, I hope you did have the time to go through those detailed balance relationships on your own. Yeah. Okay. Now in the way I'm presenting this, we've seen then the radiative transfer equation, and we've related it to those coefficients, right? The emission and the absorption coefficients in both in the continuum and discrete cases. Now is the time to introduce useful quantities, which are, for instance, the opacity, which is the same as the absorption coefficient, except that let me do something a bit better here. I'll move this on the other side. Okay, so this is the here we're introducing then the opacity, which is the same as the absorption coefficient, except that we're multiplying by the density, the mass density. Okay, this is the quantity that's more. I mean, kappa, the opacity, is the quantity that's most often used in professional astronomy, rather than the absorption coefficient. Okay, this is what you'll find quoted in textbooks. And so if you want to get the total optical depth along the ray, then yeah, you integrate along the line of sight the absorption coefficient, or else the opacity. Okay, so in other words, what we have is this. We have sorry, I've got an arrow here. On a pen. Okay, so we define that's not what I want. There we go. So we want we introduce then the an element of optical depth is defined as rho times kappa times well, an interval of length along the line of sight. Okay, so this is ds and this is s. So that is linear. So this has got units of say centimeters. Okay, This has got unit of centimeters to centimeters to the minus 3. And kappa has got units of, grams per centimeter. And kappa has got units of centimeters squared times grams to the minus 1. So the idea is that all of this is dimensionless. This is dimensionless. And so we introduced the optical depth this way. And so the total optical depth can be written like tau equals to the integral of ds times rho kappa. Okay, so one important thing to note here. So this whole thing here is the absorption coefficient. Okay, and we noted that the absorption coefficient is the density of absorbers times their cross section. Okay, now the cross section is a function of frequency, right? It's like the effective size of the targets or the obstacles, if you want, in their interaction with the photons. So you have photons flying at obstacles, and those obstacles do not always have the same size for any photon. If you have a radio photon, it's going to behave completely differently from an optical infrared photon compared to an X-ray photon or a gamma ray photon. Okay, the effective size of the target is frequency dependent. Yeah, so that's also true for the lines. If you have a photon that's not the right frequency, then it goes through an atom. Nothing happens to it. But if you shine light of a random frequency at the hydrogen atom, then light will go through unless it's got just the right frequency to excite the hydrogen atom, right? Yeah. So this absorption coefficient is dependent on the frequency through the cross section, which represents all the interactions between the photons and matter. So its cross section is in general the quantity we use to describe interactions in general. I mean, it could be electrons colliding against molecules. There's also going to be a cross section. Okay, so this is the way we represent the resulting interaction between in the scattering we're studying here. So this is frequency dependent also, and so we have a frequency dependence here, and so the optical depth is also frequency dependent. Okay. So let's put back the frequency dependence here, okay? So that's one very important thing to bear in mind. Every time you speak of optical depth, you have to say which frequency. Now, it is often the case, especially in theory, I mean, theoreticians tend to drop the frequency dependence. How come? How can they do this? It's because well, it depends on what specialty, but if you're talking to someone who does hydrodynamics, for instance, he'll probably not be very interested in the details of the radiative transfer itself. He's going to be interested about gravitational interactions, about fluid dynamics, you know, but he does not want to get too deep into the details of the radiative transfer, okay? So, that person who's interested in like the gravitational dynamics or the hydrodynamics, he or she can approximate all the details of the radiative transfer and drop this frequency dependence, this nu I've added here, by referring to some kind of average. Okay, and so for instance, we'd be more interested in the optical depth at the frequency where the material is shining. For instance, if you have thermal radiation, if you're studying a nebula, for instance, that's collapsing under its own gravitational weight, you know, like could be either a protogalaxy or a protostar, you know, something that's collapsing on its own weight, and you know, you're going to have a local temperature, and that temperature is going to lead to some thermal radiation, right? And so this frequency he knew is going to be similar to the Wien wavelength, you know, like the Wien law, lambda t equals 0.3 something. So that Wien law dictates a frequency, and theoreticians tend to drop this frequency dependence using the Rosseland approximation. So this is one of the things we want to get to at the end of this chapter, which is probably going to be next week by now. We need to understand what's the Rosseland approximation, because it's often used to drop exactly this frequency dependence. Okay, observers, we don't do this. Okay, observers, we normally respect this frequency dependence because we want to know what the appearance of an object is. You know, observers look at things on the sky, and we want to know, we want to relate the structure of the object from what we see. And what we see depends on the frequency. Okay, so we certainly will never drop the nu in observational work. Okay, I'm just mentioning that sometimes you'll come across the same optical depth, but without any subscript nu. And so you wonder, you know, where does the nu come from? And those are usually theoretical work where there's been an average over frequencies. Okay. So I see that unfortunately Nick has dropped out, probably because of an internet connection issue. But anyway, I'm recording now, so she can catch up later also. However, if you see her trying to join in and I do not react, please inform me, because sometimes I don't see the pop-up window. Okay. Okay, so that's one caveat about the optical depth. And so the other caveat, oh, here she is back again. Okay, so the other caveat, the caveat was just to say that sometimes you'll not find the frequency dependence. So I think you got me right. You understood by now that there is a frequency dependent. It's always frequency dependent. Sometimes we can do an average, okay? And this is one of the things we'll get to at the end of the chapter. Another thing I'd like to bring your attention to here, and it's quite interesting, is this one. We can rewrite this, this integral along the line of sight like this. Suppose that we have a uniform medium. So for a uniform, this is for a uniform medium, we have that kappa nu could depend on the temperature, and it could even, I mean, it could also depend on the local density, but let's assume that it's only the temperature dependent, okay? That would be constant at a fixed temperature, okay? And so the optical depth can be written as kappa nu, which is out of the integral, times the integral along the line of sight of the density. And that is also an interesting way to put things, because this integral, that is what we call the column density. So that would be in units of grams per centimeter squared. Okay, so that would be the surface density. That's the volume density, that's the surface density. And so if we put it that way, and we have this expression, that's interesting because, you know, this way we see, so the total optical depth in the medium is increases with the opacity. Okay, well, so if the medium is more opaque, it's, I mean, has higher opacity, then it's more opaque. It's kind of obvious, but it's also proportional to the surface density. Okay, so that's a useful way to put things. Another thing to note is that the absorption and the scattering lead to two different opacities. So this kappa nu coefficient can either be, so that can be either due to absorption or to scattering, or both. You can also quote the total optical depth. Which one do I use? Which one is the relevant one to tell if to report? Is the medium optically thick? Is the medium optically thick to absorption? Is the medium optically thick to scattering? Is it both? Well, which one do you use? It depends on the context. There's not a single definition of what the optical depth is. So that's another interesting property of the optical depth. The optical depth is useful to represent the radiative transfer in the source you're observing or you're considering, but you have to be very cautious about the definition of the optical depth. Okay, so you always have to be consistent, whether you're in the absorption or the scattering or both. Okay, you have to be consistent and you define it. Okay, good. Next, some other properties of the optical depth we've already discussed. So I think this is already, we've been through this already from the textbook. And the, let me remember here the way I'm putting things. Okay, so if we have pure absorption, so in the pure absorption case, we have pure absorption. What I mean is this. In this case, we have a single variable, so it's the same partial derivative, and that is minus alpha nu I nu. Okay. So if alpha nu is constant, no, that doesn't help. I'll just write it, is constant. So if then we have well, okay, yeah, I'll write it like this. I nu is I nu 0 e to the minus alpha nu s. And this here is the optical depth. Okay, so that's the exponential decay. Okay, so that's the exponential decay. So if you remember that the specific intensity can be recast as a photon density, you know, the specific intensity is going to be proportional to the density of photons. Okay, the photons are all flying at the speed of light. Okay, but it's like a stream. You know, imagine like you have like a river going to the speed of light. But at any given time in any given volume or volume element, there will be a density of water, right? Even though it's flowing, you know, you can, same with light, you can define a number density of photons, okay? So specific intensity is proportional to the local density of photons, okay? And so this exponential decay is a reduction in the number of photons due to absorption. And so we can regard e to the minus tau as the survival probability. That would be like the survival probability at S. Okay, so assuming that this is S, that we've entered the medium at 0. Okay, so that's the medium is in here, and that's his vacuum. So light is going this way. We can then calculate this average optical depth. We can you know, like well, if we how could I explain this? yeah, so that would be like a probability density function, which is proportional to this exponential decay rate. Okay. No, that's not the way to put it. No, this is good. That's going to be confusing only. Just yeah, this is correct. This is the survival probability at S, and then we define this average optical depth as the integral along the optical depth directly of tau nu times e to the minus tau nu. Okay, so what am I trying to explain here? If you do the math here, this is going to be 1, right? So that is equal to 1. And you know, you do an integration by parts, and you show that this is 1. On the other hand, this is also, if this is the probability associated with survival at this optical depth, then this is going to give you like the average optical depth for a photon, for any photon that goes through the medium. And so that is, yeah, so all the photons are going to have this, well, if the medium is infinite, so that would be an into, okay. That's for an infinite medium. Okay, so if you can do the integral to infinity, all the photons are going to be absorbed, okay? And this average optical depth is 1, okay? Means that that would be like the typical optical depth for a photon. And where does this argument come from? Is because this is the probability associated to survival at this optical depth. Okay, so it's not really an averaging, it's more like a definition. Maybe I should put another bar here. But can you see that this is indeed an average? Because like this is the probability associated to tau, okay? And so that would be like the average optical depth, and this is going to be, we can also relate this to let's write the definition in green under this. So we remember that tau is alpha times L, okay, the distance. And so this means that we have like the average optical depth is 1, means that we have alpha times an average L equals 1, okay? And that average L is the photon mean free path, okay? So that is what we will be calling the mean free path. So the average distance that a photon will travel before being absorbed, that is the average optical depth for defined this way. So I mean, we're integrating of all possible optical depth values, and we're taking the average of its of the optical depth given this distribution. Okay, so this is a probability density indeed per unit of per interval of optical depth. So that's why I got confused earlier on, because this is dimensionless, and this is also a density, and this is a density and also a probability, both things. But anyway, I'm just maybe I should insist on this aspect. So just say if you have an average of f, you do this. Okay, so that's what I meant. You know, when you're averaging a quantity, and that would be like the distribution, probability distribution. Okay, right. So this is the same. We are defining the average optical depth, integrating over possible optical depth. Okay, multiplied by tau instead of x, and this is the f associated to f. Okay. So what is the probability of association to that optical depth? Is it's e to the minus tau, in the sense that that is the survival probability of photons. So it's a bit what we're trying to say here is that this for photons to reach a given optical depth, they have to survive absorption all the way through. Okay, so like if photons there's lots of photons coming in like this, some of them are going to survive up to here. Okay, and like the probability of survival all the way here is this exponential decay. Okay, and so this coordinate S, you can write it in terms of the physical coordinate or in terms of the optical depth. You can recast this S, or alternatively talk about tau, because they're proportional with the absorption coefficient. Okay, and so when I say what is the probability of reaching S or tau, I mean what is the probability of what is the survival probability of the photons. Okay, so that is what I mean here by averaging this optical depth. Okay, it's the optical depth that can be reached by the photons, right? That's what we're trying to represent here. Okay, so I'll have to leave the class at this stage here now, because I've got my appointment, as I explained earlier on. So I have to run right now, but we'll meet next Tuesday. Please make sure to go through chapters 1.7, 1.8. This is really difficult material. You'll see that you'll run into several conceptual issues. And please ask questions next Tuesday so we can go through them, okay? And in parallel, I'll try to cover the same material that through in my perspective. Ciao, Felipe. Bye, Nitya. Bye, Pratush.
Bye.
Thanks for connecting today. Let's meet next week.
Bye.
Ciao.
Yes.
See you Tuesday.
Ciao.